Hey guys, how's it going? So today we're going to be taking a look at this paper called Learning to Summarize from Human Feedback. It was a paper that was produced by OpenAI, I think in 2020. It was quite an interesting paper. I think with the rise of ChatGPT, we saw the potential of using reinforced learning with human feedback. I think like these type of techniques they excel at like trying to align the model with human intent. Hence, these models tend to be good, like ChatGPT, right? The specifically why I'm covering this paper is because they were able to open source the code, so we get to understand what they did, right? Because of I feel like this architecture, as some of you might have came across the learning what is it, reinforced learning with human feedback, and you will see that actually the diagram that you see on the screen is quite similar to that one, right? They're just the same, honestly. um, so yeah, we will try to understand this. Just to brief you how things will go, I'm taking a different approach from going on, guys, which is that I'm no longer going to cover like the paper. I'm going to be covering the code, but what I'll do is that I'll just like have these snippets from the paper so that we read the important things at the same time we link these things to the code. But like 80% of the time will be on the code, right? This is just so that as they say that the devil is in the detail, so we get to understand actually what they did, the actual thing that they did was. Um, yeah, this code, I won't lie to you guys, I feel like it's quite complex, at least for me. It was because it looks like actually they did everything from scratch, like literally everything was done from scratch. How they had to shut the model, the transformer, the attention, how they had to shut it and distribute their training processes and stuff like that. So all of that they had to do that from scratch, as you can see from also these encodings, and they don't import any libraries. Everything is just like from scratch, right? Okay, maybe not everything because they still use Python and PyTorch, but you get the point, like all the main stuff, right? But anyway, yeah, so it's gonna be quite interesting. So without wasting any time, let's get into it. So just gonna walk you through this diagram so that you have some sort of like an idea of like what's going on. So when we say collect human feedback in this context of the paper, because of here we're trying to summarize given some sort of like an article or post, but in this case they were using a Reddit post. So from a Reddit post, we try to get summaries. So what we'll do is that we use a policy which is going to generate the summaries given this post. Then the human is going to take those summaries, right? The two of those summaries, and it's going to select which one is good. So it's more like a human is a judge. So it's select which summary is good that has been produced by the policy. Okay. Then we train a reward model, right? So we can think of like we have a post with a summary, right? We have two posts and summaries here. Then we pass them to the reward model. So the reward model essentially is going to calculate the reward for each summary, right? Then what we do is that we're going to calculate the loss based on the reward and human label. Then we update the weights of the reward model. By doing this, essentially, we're trying to teach the reward model to be able to be good at knowing which summary is good. So it can be able to, given the summary, can tell you this is good and can give a reward. So I keep on using the term policy, and I keep on using the term maybe function, value function. I just want you to know that these terms are coming from reinforcement learning. So a value function, essentially, you can think of it as like it estimates the expected cumulative reward, right, that an agent can receive. Then, on the other hand, you can think of a policy as a function that takes the current state of an environment as input and output in action to be taken, right? That's what it is to this, right? So I'm just telling you this so that if you it happens that you go and read the paper, you can see that the author keep on using these terms a lot. So especially if you're someone who's not coming from reinforcement learning, you're just like me and you're just like into transformers and deep learning, and you might like deep learning is quite broad, so there's more things into it. So some of you might not actually work with reinforcement learning, just like me, a lot. So anyway, that's one thing that I needed to explain. Continuing, then the third step is that we have a train policy with PPO. So what you can think here is that we're gonna sample a post from our data set, then the policy is going to generate a summary of this post, right? Based on this post, then the rewards model that we trained here essentially is gonna calculate the reward, then the reward is going to be used to update the policy, so right, so that it can get better and better and better at generating good summaries. That's what it is to this, right? So that's what it is to this architecture, this architecture that is here, right? I know that some of you might not still be understanding this, especially if it's the first time. So what I'll try to do is that I'll keep on coming back to this architecture and then make sure that you have a good grasp as much as we keep on going. So, but yeah, if you have a good grasp of this so far, then that's good, right? So, without wasting any time, let's get into the first component, which is going to be the data set. Some of you might redeem this as unnecessary. Maybe some of you might really want me to jump into like the actual things, but yeah, I'm just gonna try to kind of like cover the details or the most important things. Some of these stuff, like how the data set is getting shaped and how they do the data cleaning, these things they get overlooked. I feel like, especially in the paper, or we don't talk about this stuff. But really, to think about it, like these are the like the core component that makes these papers to be possible. So I think it's good that we understand how the data cleaning process works and how the Python coding works, right? So let's get into this data set and just try to understand how it works. So we have these n tokens, guys, right? So I think these n tokens will be used to kind of like end the sentence. For instance, you can see that we have a period, we have a question mark. So we're gonna see if, like, given a sentence, does it have any of these, right? So if it has any of these, then what we're gonna do is that we're gonna say, okay, that's the end. If not, then we're going to try to edit, right? So, and this is the function that does that. So we can see that essentially we take in the line, we can think it's a sentence. Then essentially what we do is that we check if the last component of that sentence, whether it's a word or anything, that's the last thing on that sentence. We check if it is in the end token. If it contains one of these things, then we're gonna return the line, because obviously it has already has a period, or it has already has a question mark, so that's the end. But if not, we're just gonna add this period to show that it's the end. We will, maybe as we go on through the code, maybe we'll understand why they needed to add this period. Maybe we'll actually understand why they needed to do that, and that's get a better context. Anyway, then they we have this cleanup highlights. We can see that we also take in the line, which is a sentence in this case, and we can see that what they're doing here is that we're trying to split the line, the sentence, to say that if it contains this, like, right. If it start with this, what we want to do is that we want to take the second part. So we want to omit this. That's what I think this line does. Then we have the bad prefixes. So here, I think also we're just saying that if it start with these bad prefixes, we're just gonna return an empty string. This might be because of we don't want anything that has these. By the way, guys, I would just want to iterate that this data set was kind of like, I think it was also taken from articles. So obviously, like when you extract data from articles as raw, you're gonna get all of these stuff like advertisement and stuff like that. So it's definitely normal for you to kind of like process the data like this. So just note that, right? I think if you wanna have a glance of the data set, you can go to this link. I'll just link them in the description below so that you guys can have the data set. But usually one thing I know is that when you're cleaning your data, it's based on the trial and error, right? So because there's so many articles, you don't know what will come up. You just train and you observe, then you see, oh, okay, actually there's this thing called click here, I don't want it, then you write the code to do that. So you iterate. So so that's one thing, right? Anyway, then we remove that, the bad practices. So what could happen is that we could be having these click here, which we also don't want. So what's going to happen is that we going to we're going to check if these bad things here are inside our line. Then we're gonna split the this we're gonna split our line by bed, and we're gonna take the first string. So we omitting this. Okay, then we returning the line. I hope that makes sense. Then we say get article and highlights. Okay, so what happened is that I'm thinking that here we might be, because of this is a supervised model. So I'm thinking that we're trying to use the supervised. We're trying to use the highlight as our summary. So we will try to understand. So we might be get the article, which will be our more like our post, then the highlight, which will be more like our summary, right? That might be what's going on here, but let's try to understand and see. So we open the file. Definitely, we read it in as the original text. Then we have this function here. I think this function is also applying some data cleaning stuff. Looking at this, the author wrote that this was not handled by this function. So I'm definitely sure that this I don't know this library, by the way. I think it's kind of like doing some data cleaning, removing some of the instances that we don't want. So yeah, that's what it is, right? So but yeah, so we can see that it did not actually handle this. So that's why here we replaced that with an empty string. So that's the original text. So I'm just gonna leave a comment here just for you guys, and so it's part of data cleaning and me just removing some text, removing some instances of text. So I don't know, but yeah, I'm thinking that's part of it, right? So just bear with me. Some of the things there I might not have idea, but I'll try to kind of like link the link for you guys to kind of like go through. Anyway, we have these article lines. So okay, we're gonna see what we're storing inside there. Then we have highlights and has seen highlights. Okay, then we say for line in original text, then we split this by line. So we're gonna think of like we have a line. So original text could be a paragraph. So paragraph is multiple lines. So here we're getting one line. Then we check if the line is empty or it's an empty string. Then we're gonna continue. Then if the line start with add highlight, we assert that line equals to highlight, then has seen highlight equals to true. So we set this has seen to highlight equals to true. Okay. Then we say else if has seen highlight, which is this is if this is true, then we're gonna say if clean highlights, we're gonna say clean highlights line. So we're gonna apply this function to this, right? So we're gonna clean up the highlights by applying all of these stuff that we explained. Then we're gonna get the line if not refs with bullets. Um, then we're gonna say okay, line equals to fixed period. Then we're gonna apply the function to fix the period. If line highlights dot append lines, so we're gonna append the lines to this highlights. Okay, then else articles append lines. So what I'm seeing here is that essentially we're gonna loop through the paragraph, right? Then we will try to append this paragraph. We're gonna append a line inside the articles, right? So because if it's a for loop, you can think of we're gonna go each line in the side of paragraph, but at some point inside that we're gonna get to a line, and the line will start with this, and that's where I think it's gonna be more like a summary. And then we're gonna say has seen highlight equals to true, right? If has seen highlights equals to true, it's gonna go again in for loop. Then we're gonna apply the data cleaning. So my assumption here is that okay, I know that I might have confused you there, right? Let me just try to do some sort of like explanation based on the data cleaning here. So let's say we have a line like this, right? It's a paragraph like so. So I am thinking that what happened here is that we're gonna get an add highlight like so. So right, and when we see it like so, we gonna set the highlight equals to true. So this will change equals to true. Maybe let's say we had another line. We go again, we grab the new line. Because of this has already been true, what we're gonna do is that we're gonna now start to clean up these and append the line to the highlights. So which means that this this text that is gonna come after highlight is just the summaries. That's why we're adding it inside here. Okay, I hope that gives you much more sense now, so that you understand. So that's what I'm thinking happened here. So now you can think of like we have like the the cleaned data inside here of the summaries, and we have the lines inside here, and the scene line is just for us to know that we've reached that line that has summaries. Okay, okay, then we try to join these by lines, which is cool. Then we clean up start. I've never came across this. Did you guys see it? I have didn't see clean up start. Okay, there's it here. Okay, so we take the article. So this is so we have article lines and we've joined them. Okay, now we have just one big giant. So what we do is that we apply this clean up start. So here we try to split the text, right, based on this condition. So if we get to match the CNN, then we're gonna split and we're gonna take the second part of that sentence. So here you can think like we have a paragraph like so, right? Like we have a paragraph, then within that paragraph there will be a point whereby we have the CNN and the paragraph will continue, right? So we don't want the first part, we're just omitting that and we want the second part of the paragraph, okay? So like I said, this is based on observation, purely observations. So this the author could have realized that maybe the CNN, maybe they're just talking about it's nothing to do with the article, maybe it's just something to do with CNN or something like that. Anyway, then what we do here is that we we try to detect CNN, this time without no dashes, but instead there's the CNN. All right. Then we say this CNN is within the first 100 characters of the text, right? It's gonna split like we did so, and it's gonna select the last one, right? Then it's gonna add the text. It's gonna add this to the text going forward. Okay, so I know this might be confusing, but let me try to kind of like show you guys from an example. So let's say we have a text paragraph like so, right? Then we say that we have reached the 100, like let's say here it's 100. So there is another text going forward here, greater than 100, right? But we are cutting here at 100, right? But we are saying that within this 100, if you see CNN, within this 100, if you see a CNN, break it into two. We don't want the CNN part. So because you see with this minus one, we're gonna select the second, the last part. So that's what this means, right? So let's say here we cut off maybe at 80, something like that. So 80 going forward, that's our cutoff, like because we selected the last part. Maybe this part here, 80 downwards, it has a CNN, so we didn't want that. So which means that we're gonna go from 80 plus 100 plus. So we're gonna go from 80 all the way to 100 plus. We're getting all the other paragraph that we didn't get. So that's pretty what they did here. Then here we're trying to say, okay, we're gonna split this by the text contain any of the updates. We're gonna take the last part. So yeah, then we replace all of these things here with this with this parenthesis. Yeah. So then we text dot strip to remove the spaces. That's what this thing does. I think we applying it here at the articles. Okay. Um, Yeah, I hope that makes sense. Then it says refs with bullets. I think here it's just referring that we have this, then we're gonna add this, then after the new lines, we're gonna add this, then we're gonna join by the highlights. So reference with bullets. So if this is true, we're gonna do this. Then it says else highlights equals to, we're just gonna join this by empty space. So we return the article and their summaries, so which is fine. Okay, so that's cool. What's next? What's next? I'm just gonna, some of these functions are being referenced in the larger functions. So what I'll do is that I'm just gonna leave them because we're gonna come back to them. because I think like it's nice when we go to these functions when they're being pointed towards. So here we have the split, we have the subset, we have ref with bullets. Uh, we try to open the blob file. Okay, we try to open the blob file. Then this is like the URLs dot strip for lines in and this. Then we take that line and we strip it. Then this is gonna be our URL. Then we also have a blob. Open this JSON file. Then we get these titles. Then we have these download cache. I'm just gonna open this folder so that we see actually what's going on here. Uh, so we have this, but I'm thinking that this is just like reading the data. I'm not gonna go into too much detail because it's just like just getting the data from the file. So download directory cached, open file cached. Okay, there's it here. Yeah, you see. So it's just like a BF. I think this is just a blob file. Then we just like give it a path and a mode uh, and we open this file. I think, but we yield it. So that's what I think we do here. Um, then we say for URL in URLs, which is coming from here. Then we say URL get URL info, which is this. So this is just gonna check if this URL contains any of the daily mails or mail on Sundays in Yahoo. Then it's gonna say site is called to Daily Mail. Otherwise, it's gonna say site is CNN. Um, then we're gonna hash this URL. Then we're gonna return the site and the URL hash. So I think the URL hash is used uh, to identify the URLs. Okay, so uniquely identify the URLs. So that's what we're gonna get, like the article ID. So which is quite good, right? So this is quite a good technique. We can see that these guys they kind of like creating an article ID and they're using this hash function. So that's what we're gonna get here. That's why they're calling it, I think, article IDs. So yeah, this is what we're doing. Where were we? We're here. So we have the site, which could be the daily news, whatever the site is. Then this is the hash. Then we say os.path join um, URL directory, then the site, then storage, then we provide here the article ID. Okay. Okay, then we have the path, then get articles and highlights. We call the function that we went through. We path it all the data by pointing it to the files. Then we get the articles and ref sense. Get articles and highlights just to make sure. Yeah, that's correct. So I was confused because yeah, they say ref sense and yeah, it's just saying highlights. So yeah. Anyway, that's that. Then we have the article reference is called to ref sense and article ID. We have the sites. We yield them inside the dictionary. Okay, so let's look into the encodings. So this is like the byte pair encodings and bytes to Unicode functions. So before we get into like byte pair encodings, and I'm just gonna explain it. Also, I'm gonna skim over it because of we have so many files to cover. So but the goal here, before we get into the code, I'd just like to give you a high level overview of like what is like byte pair encoding and what is it that we're trying to accomplish. So I usually think of this like more like a data compression algorithm, so maybe technique. So essentially we have text data, and we try to replace the frequency of the frequency of words occurring within the sequence, right? With like smaller representation. I don't know if that makes sense. So let's say for instance we have some sort of like TE and we have a text and TE is always occurring together. So we're gonna try to combine these two. So it's gonna become one word in our vocab. So let's say vocab is probably made up of like these characters like A, B, and C, right, and so forth, right? So but we realize that actually when we try to analyze our data and we calculate the frequency of these, and we see that for the most part, actually, our text looks like it contains TEs always coming together. So we're gonna go to our vocab and we're gonna add TE to that, right? So this will then be used uh, more of a token, so that given a text, we can actually use this instead of like using TE, right? So this is much cheaper because you don't have a lot of tokens, like you've compressed data. So how it works is that you're firstly going to initialize the vocab, right? So the first step is to create a vocab with all the unique characters in the corpus. So you can think like A up to Z, like so, and uh, yeah, all of these what is it, unicodes you wanna add, like stuff like that, so you can add them. So then what we're gonna do is that we're gonna count. I'm just doing it this way so that you kind of like think of this as a sequence of steps. So the next thing is going to be the count characters pairs. So here, what we do essentially is that the algorithm counts the frequency of each pair of adjacent characters in the corpus, right? So, like I said, that if TE occurs the most, then it will be kind of like matched, right? And which is the way to match kind of like bring us to the third step, which is that here we try to match the most frequent pairs, right? So match the most frequent pairs, right? Um, yeah, into the vocab. Like I said, then this thing's gonna be part of the vocab. So vocab. So we kind of like iterate through this, like this thing, iterate through the steps so that we kind of like reach the point whereby we okay. Reason being is that maybe you can find that okay, actually we missed TE, but TE also is still occurring maybe with like I don't know, maybe with like R or something like that. Then we're gonna merge TE with R. So we're gonna continue to do that because they occur the most, and this help us kind of like right. So we have feel it's data compression because imagine like you were going to assign these T to each number, but this time you assign one number. So that's what it is, right? So that's that. I hope like my explanation probably wasn't the best, but the one thing I hope it did was to kind of like give you a high level overview. Um, So what's going on here is that we have the byte to encode. So here essentially we can think of like we creating this async characters, right? And then we're gonna have to link these async characters to bytes. So it's gonna be bytes and characters, right? So let me show you from an example. I think like we understand better from examples. So we can think of like we have this, we're creating this variable, maybe let's call it B2U, then we're gonna say equals to bytes to Unicode, which is gonna take this, like so. Oops. Okay. What was that? It was oh, that's nice. Control B. I didn't know about that. Anyway, that's cool. So you have bytes to encode. Then what you're gonna do is that you can actually call B2U, and you can pass it like some sort of like 64 something like that, right? Then this 65 or 64 is gonna return probably like A or something like that, right? So it's gonna give you the correct one, right? And your question might be like, but like, can you provide any number into this byte pair because of it's a dictionary here? You can't. Like I've commented this to say that there's 256 um, possibilities that you can pass inside this byte to encode. So we can pass any value from 1 to 256, right? I think we're starting to index from 0 to 255 in this case. So it's going to be 0 to 255. So that's what we do, but these create these async characters, and some of you might be quite curious what these are. So from here, from this character here, we're gonna look through all of these, and we're gonna create this CE. So I'm just gonna paste here just to show you an example, like a similar CE. How will these things look like? It will look something like this. then we're gonna link them to by pen. That's what we're gonna have. But yeah, the point is that given the bytes, you're gonna encode that. Okay, Unicode, you're gonna kind of like send that to Unicode. But yeah, that's that. I wanted to say, you can go through this code, uh, but it pretty much does what I kind of like explained at the high level, like so. So yeah, you can go through it, but it's yeah, it shouldn't be that hard because of if you pretty much understand like that workflow, then it should be fine. So the thing is, as you guys can see, like I'm not trying to be to cheat you or something like that. It's just that we have so many files, and some of you probably want to go through the reward and policy functions. So yeah, that's what I wanna kind of like get out of the way. So these are just tests. So don't worry about these files. They're just tests unless if you wanna just drill into them. So these are just tests. So I'm gonna close the data set now since we have a high overview of how it works. So this init file is empty. So we're just gonna go straight to the attention and let's see how it works. So essentially we have this D model which will represent the dimensionality of the input vectors, and I believe that this is context. So this should represent the length of the input sequence. Then we have this the attention, which is going to be the size of the hidden states. Um, then we have number of heads, and these are just used for dropout. Um, so what we do is that we're gonna see a lot of things related to sharding in this code. Mainly, this is because of like some of these attention or some of these components that we'll be covering will be running on different processes. So there has to be a communication between these processes, right? So in this case, we have this and shard, and we want to shard the attention. So what we do is that depending on like the number of shard which is coming from MP communication, I'm gonna cover this in more detail when we get to the layout. So we divide the attention dimension by the number of shards. So we can think of like the attention dimension, it's been sharded, right? So then these self dot queries and value will be projected to the sharded attention to the sharded attention dimension, if that makes sense, right? So that's that. Then we have this function called attention function, which I'm just gonna scroll to that function in a second. Yeah. So what we have here is the ascension function, which we take the query and key and value. So this is a typical attention workflow in which like we have to split these queries into multiple heads. So we call this also, I think, multi-head attention. So the function to do this, it's just this here, right? So we split this. You can think of it as like we have a word, and each word is going to have query, key, and value, right? Then those query, key, and value will be split into multiple heads, right? We do this just to get a better context. And the dimension of this query key will be like so: batch, head, NQ, and D model, you know. And what we do here is that we have the software scale, which is 1 divided by NP square root of the dimension of query, right? So then we multiply this by the query and key. So this is just the scaling factor that we apply to the key. So this is typical workflow of the attention. So we have the matrix multiplication between the query and key. We don't have to do transpose, mainly because as you can see here, we this is how our input looks like. So you can think of like these models gonna cancel one another. So we're gonna be having something like batch, which is batch head. What is it? NQ, right? Because of this here, we did a matrix multiplication. Then this should be NK, like so. Right. So that's what we have. Then we have the W type, and we take this W type to be float. Then here we have we extract the size of the NQ and NK, which we were correct with the dimension here, because that's what it looks like. Then we try to mask. So An autocorrective mask essentially is applied to attention score to prevent future tokens from being attended to. So this trial essentially does that for us, right? So I'm not going to try to explain or try to visualize some of these functions. Like, just watch my transformer video. I think I try to visualize these and draw them and how they work, right? So just do that so that we don't make this video to be long, right? So if you don't understand. Um, then yeah, as the author 30 says that we make all the values where the mask cost is 0 into infinity so that they get ignored when we do a softmax. So we don't they're not gonna be attended when we apply the softmax. And here we get the scores. Then we say self dot dropout module, we apply the dropout, then we take the weights and we apply it to the value. Then we get this attention here. So this attention is going to be having batch, head, and cube by D model. Then we merge all the heads, which is we're applying this right here. So this should be this function here. Okay. So what will the dimension be then in this case? So it looks like we're gonna cancel this head dimension. So it's gonna be b by nq by d model, right? Because we're concatenating the heads using this function. So we can see that from this here, we essentially multiplying these two, right? So yeah, that's what I think it will happen. So we're gonna have three, three, three values at the end of the day as per the new X shape. So that's that. That's like the attention. I know that for some of you, if you are new to this, it might seem like I didn't like say anything, but honestly, for those like you watch my attention transformer video, you'll understand a lot because sometimes like going through the code without the intuition, it might or like explaining the intuitive behind it, it might not make sense. So there, at least I try to explain what is the purpose behind such things, right? So check it out. um, what we're gonna do here is that we're gonna go through the loss function, which is this. So the function essentially computes the softmax cross entropy loss given the batch of logits and the corresponding targets. So here we're going to take the targets and flatten them, including the logits, right, which were coming from this outputs and B. Then we apply this toss cross entropy with this reduction. So this reduction means that we will compute a loss. We will compute the loss and average it, right? So this will return a scalar loss. So what you can think of here is that we're gonna return for each batch, we're gonna return a loss, right? So we're gonna see how this plays out as it's gonna be used in what is it query response code. I think we're still far from that, but yeah, just know that there's this, but we're gonna come back and reference it if like maybe there's something that confuses us, especially around the dimensions. So the next file that we're gonna look into is this file called sample function. So this is a file that is gonna be referenced quite a lot. It's just for sampling. So for instance, here we have this function called standard, which takes in the temperature. So you can think of a temperature as it controls the temperature of the softmax, right? So it determines like how much the logits are softened, right, so to speak. So for instance, like let's say we have a lower temperature, this could result in a more peaky distribution, whereas with a higher temperature result in a more uniform distribution, or more exploratory, right? Then these lodges, you can think of them as they represent um, unnormalized log probabilities, right, in a neural network. Okay, so we have these lodges, then we're gonna divide them by this temperature. Like I said, when we divide them by this temperature, we try to soften the lodges. So depending on like what we're passing here, uh, it will depend how we want to soften that, right? Then you have this function here, just converting this to a float. But anyway, we have this torch dot distribution categorical. You can think of this as like we trying to create the probabilities distribution of a discrete categories using the softmax. So we're gonna sample from this distribution, right? Given these logits, okay. Then we have this Armax, which you can think of it as like some of these techniques. They are called greedy decoding. So meaning that this is just going to select the maximum value of the largest. So there is no trying to be creative or something like that. You just select the best value. That's it. That's what it is, right? So yeah, it's called. I think it's also called greedy decoding. Okay. Then we have these nucleus sampler. So we can see that the author also here says that the P of 0.9 means that the top 90% of likelihood weighted options are considered, and the P point zero zero is equivalent of Rmax. Okay, okay, I get that. Then we also here we have pretty much a temperature. Then this top P, it determines the proportion of likelihood weighted option to consider. Then this, yeah, this is the top P, so it's the same thing. So this, if this is one, if this is zero, then we select the best. We apply this. If this is if this is one, then we apply the standard. So with the standard function, okay, given this temperature, then we have this sample function inside this nucleus sampler. So what we do here, just to read what this says, it says that remove lodges that do not represent the top proportion. Okay, yeah, it makes sense because of we want only the logits that are within the top P, okay, because that's where we want to sample from, okay. So what we do is that we clone this, we create a copy of these logits, then we sort these logits, right, in a descending order, so from the highest to the lowest. Then what we do is that we have this torch.cumsum. Essentially, we do this over the softmax of the sorted logits. So you can think of like we have like the highest logits all the way to the lowest in a sorted order. Then we apply this cum sum, which is going to sum them going all the way down. This is because we want to say that where the cum sum is greater than top p, these are the indexes that we're going to remove, right? If this is confusing, so you can think of it this way, like let's say we have zero point 0.9, like 0.7, 0.7, 0 0.2, 0 point something, 1, etc, etc, etc. So when you compute these, right, you're gonna get, let's say here, you're gonna get 0.9. And if you continue to compute, you're gonna get 100, like, 1, something like that, right? So when you continue, you're gonna continue to increase the value, and we don't want that. So anything that is greater than that, we don't want that. So we just want anything that after you've accumulated, anything that is still less than 0.9, because obviously they're sorted in a descending order. So we're gonna start with the top, with the top top values, right? So here we just like going to remove those. Then these are just the indexes to remove, which we set them to touch.0 like based on taking the shape of these logits. Then we pass in the logit in this standard function with this now with this temperature, and we return the sample. So that's what this will do. Uh, Help us to sample. Then we have these operations which we're gonna be referencing. So here, what we're looking at is the activation functions. We have the switch, quick value, and these are some of the activation functions. I think this is just we put them in the dictionary so that we can easily get them. Then we have this conv1d. I think we use this in the attention module, um, which we take in the input and output. We didn't actually try to go this function, but we kind of like understood what it's doing, given the function that we're working on. So yeah, this is our operations. Yeah, I think now let's go to the. We're gonna cover the models now. So we're gonna look into the what is it? I think let's go to model layout. Then we can go to other rewards and policy functions. Okay. So we have model layout. Essentially, it's going to hold the structure of the model and the current rank position within it. So um, like how distributed system work is that or distributed training in a way is that let's say we have a model and that model does not fit in one GPU, so we have to shard it, meaning that we have to split it uh, and and distribute this across different GPUs, right? So here, the number of shard is going to represent, given the full instance of a model, how many times we want to break it, right? So that we can share it across these GPUs. So what we have here is the total GPUs that our system have. Then we have this my rank, which will be the current rank, right? Then we create this rank depending on the number of GPUs. So which means that the rank will be assigned to a GPU here. Okay, then here it says GPUs per replica. So, and we assign this to a number of shards, which makes sense if you think about it, because we're gonna need GPUs to hold this number of shards, meaning that you can think of a replica as a full instance of a model, but it's been sharded. So for us to hold that model, we need this number of GPUs, right? So it's fine to assign this to each shards. Um, I've already made this here. I've just wrote this so that make an example so that you guys can understand. I think this might be confusing a little bit, but let's say we have 32 GPUs, right? And we have replicas per GPU, meaning shards, which is four. Then we're gonna have eight replicas. You can think of this eight as like the what's this? So you can think of this eight as like the full instance of the model that we distributed across like multiple GPUs, right? So here we're gonna have the rank because we have to reshape it based on the replicas that we have. So we're creating this matrix which we whereby we're gonna say replicas and shards. So you can think of this replica as each row represent an instance of the model, and then each column is gonna represent the shard or a set of GPU assigned to the replica. So, for instance, let's say we have like eight here, then we have 8 by 4, right? So for each replica, then we're gonna have four GPUs, right? So we have eight replicas, and for each year, we're gonna have four GPUs, right, assigned to it, which makes sense because the overall GPU that we have it's 32. So yeah, that's that. Then we have this init function, which I think it's gonna take in the my rank, which is the current rank that you're currently on. Then you have this total GPU, and this is based on layout dot size. Right. Then you have self dot all rank, which is also self dot total GPU. Then we spoke about this. We said like here the rank just depends on the number of GPU that we have in this case. Then we have layout.shape, which makes sense because of the rows, the replicas, and this is this is the shards, which is still fine. It's just that I said it's just number of GPUs, which is fine because of anyway for one instance of a model you need like four GPUs, so that's fine. That's what I made example as. But anyway, that's okay. What do we have here is just the warning to say that using four is currently slow because we do not have implemented this. Okay. Then we within our layout we have my rank, Then we get the replica indices and the shard index. So given the this is a two yeah a two this is this matrix, yeah, this is this rank that we have here. So this is a matrix. Then within that matrix we want this my rank, and you're gonna get this setup. So you're gonna get a specific replica ID and a shard ID. That's the point that I'm trying to raise in this case. Then you convert this to an int. Then here you have your siblings rank and my siblings rank. Yeah, I don't think some of these are quite that important, but that's like I think that's that I needed to cover. Um, so yeah, I think we can go to this function, which is query response model. So this code is quite a lot. It's like 700 lines of code. So I'm gonna try to skim it over also, but it's very important. This one is like the crucial. I feel like this is the core of the project because like it's being used across like reward model and policy. I just want to show you something. Let's go back to the paper, which is we can see that they say that where's this? Was it here? Let me just do that. Okay, supervised model. So I think it was here, right? So they say that for the PPO value function, we use transformer with completely separate parameters from the policy. So this prevents update to the value function from partially destroying the pre-trained policy early in training. We initialize the value function to the parameters of the reward model. In our experience, the reward model policy and policy have the same size. So they use the same code, even though they do not use the same parameters for the value function, because they use the as they state here, they use the separate parameters of the from the policy, but the code is still pretty much the same, and which is what I was referring to, which is this query response model, which we're gonna get into. So we're gonna start with this sample function. So this function here, essentially, we have to sample the tokens as like we're gonna use this. We have to sample the new tokens given the logit. Uh, so some of you might still remember this function, but before we get into this, let me just kind of like walk you from scratch. So we can think of this as like we have a context, which we can think of it as like a tensor containing the initial context for each batch, right? So the shape of this, it's gonna be batch by context, right? Context. I'm just keeping these shape here so that we kind of like understand some of this code. So a batch, we can think of it as like the number of sequences in each batch. In the context, we can think of it as like the length of each sentence, right? Then we have this sample length. I'm thinking that this sample length refers to the tokens that have to be generated, right? And some of you might be like, I thought we were sampling. Why do we have to generate tokens for here? So looking at this, right, just I'm gonna come back. I just wanted to explain this quickly, is that we have to loop through all the way from context to sample length. So, and as we loop through, we just keep on generating this new token. And after that, we're just gonna have to add all of these tokens and return them. And these tokens have been sampled, meaning that these are like the next generated tokens, right? So that's what it is to this. Then we have this sample function. Some of you might still remember this, but essentially, just kind of like go through it again. So this was the sample that we covered, whereby we have to sample given the logit, and you have to kind of like select. We have like nucleus sampling, Armax. We explain all of that, right? So this is gonna sample the you can say, yeah, the best token, so to speak. Then we extract, given the context, this we're going to extract the shape, which is the context, which means that we write about the concept, the context, and the badge with touch no red. We do not accumulate gradients in this case. What we're going to do is that we're going to pass in the context, and we're going to get the output, right? And this output is going to have the hidden states, and we're going to detest this. Then from this output, we're also going to get the logits, in which case this is -1 all the way forward, which means that we will like to get the last logits, right? That's why I think here they're calling it previous logits, because it's -1 and going there. So what we do here in this case, we're going to pass the previous logits, right? And we're going to get the new token. Then we extract these new token and new logic, and we call them new token and new logic, right? And we call this function, I don't know if some of you can still remember this, but essentially this was the loss function, whereby we pass in the logic and the token. So this is going to tell us how off we are with our predictions. um this was the cross entropy loss that we just gonna also kind of like browse through it so that you can remember this. And we predicted that the what is it? Um, the returned shape should be batch and loss, meaning that it should be batch by one, right? Because of the loss has been averaged across the batch, which is looks like this is the case because we have new token dot shape, which is this the case. Um, then we append the new token and the new log props, okay, to these lists here. Okay, so this is quite interesting, whereby we have to pass the new token that we generated to the model, thereby we're gonna get the output. Then we update the previous logic with the logic that we just got from the new token. So like so. So we're gonna loop through again until all the sample length. So the goal is to generate the token all the way to the sample length, right? Then after we are done, we're just gonna try to concatenate these and all including the log prop. Then we're gonna return them in its form of dictionary. Okay, that's what I think this function try to implement. Okay, so now going to the multi-head model with heads, not multi-heads, it's quite different actually. So essentially this model with heads is it takes the model and the scalar heads. So the scalar heads, you can think of it as like they return the, the scalar, like a value, right? A score. So we take this model, which is a pre-trained model, then we these scalar heads we create this self.scalar heads name, which we're gonna loop through for each head, right? We're gonna create this touch.annual linear model, which we're gonna take in the D model, the dimension of the model, and we're gonna put one. So you can think of like at the end of this model, we just need to add this head, right? So uh, we initialize the model, these heads weights with like this normal distribution, right? Because of that standard deviation. Then we include also the bias. Then we add this head to this touch.nn dictionary. So we have a name and the head here. So this is just gonna hold all the heads, including their names, right? So then we're gonna the input is gonna be passed through the input is gonna be passed through the pre-trained model, and the activations of this will be extracted. Then these activations are gonna be passed towards each head, which is gonna return a dictionary along with the original activations, right? So, like I said, that the goal here is to try to link some of this code that we're looking at to the paper so that we get to understand in a much more good way. So, if we look closely at the reward model, they say that to train our reward model, we start from a supervised baseline, right? As described above. Then add a randomly initialized linear head that outputs a scalar value. Okay, we train this model to predict which summary is better as just by a human given a post. If the summary preferred by a human is this, then we're gonna get into the loss when we go to the evaluating the reward model, right? So the scalar output of the reward for post X and summary Y with the parameter and data set for judgment. At the end of the training, we normalize the reward model outputs us that the reference summaries from our data set achieve a mean of 0. Okay, so this function here is going to output the score. So here, this multi-head model with heads is going to be embedded with the reward. So because the reward has to produce the score, right? So we're gonna see how it works from the perspective of like when it's given the what's this? When it is given the inputs and the outputs. So how does it generates the score from that perspective? Okay. So I'm assuming that this model, because of we still have a long way to go, we still have a long way to go. So we'll probably come back and refine this. So I am thinking that the model has to take in the post and the summary, right? It's just that this code here refines the model to add the heads so that it can be used as a reward. So this is going to take the post and the summary, then it's going to output the reward, right? So that's what it's going to do. But it's still in the early stage for me to make such broad statements. So what I would like to do is that I'd like to see a lot of code so that we can be sure of what we're saying. Okay. So let's continue now. So I'm gonna skip this because of this is the model spec, and this is like we save the exported model. Uh, this has to do with like the dim to shard and parameter name for shading dimensions. So yeah, I wouldn't pass this if it was I think it was quite important. Here we're just loading the exported model, so and we're saving the state. For instance, if the model include input embeddings, we load the state of that. This include the residual blocks, the final layer norm, the output embeddings, and this also include the model heads. Okay, so the code that we need to get into is the split query response output parts. So here we're told that we're given an output X with the shape, which is batch, number of responses, query length, and the response length. So it looks like the query length and the response length have been added together. So the goal now is kind of like split them apart. So what we do is that we check if the dimension is equals to 3 or greater than 3 because of we need to make sure that at least it is 3, right? Because if we're trying to split, otherwise this wouldn't work. So we store the rest of the dimension inside this rest dimension, right? Then we create this empty dictionary, which I think we're gonna upload something. So what we do is that we check if the query length is greater than 0. If it is, what we're gonna do is that we're going to say starting from the query length -1 all the way forward. So this is essentially taking the response length. So you can think of like we not starting where the query length start, but rather we're starting where the response length starting. So this way we get to get the response. So if the query length is not greater than 0, then we're just gonna store the touch. We're gonna store the NA for the response length. Okay. Then what we do here is just gonna loop through the rest of the shape at the same time while we add a dimension to the response pairing mask. Okay. um yeah, then the responses look like here we're just gonna add a mask, so we fill with NA in the place where response had pairings. Okay. That's fine. Then we return this D, which is going to be holding the responses. Yeah, I know this might not sound interesting, but yeah, let's just continue and get to apparently the code that maybe is doing something, because these are just the functions that we'll be referencing. So I like to kind of like explain them where we are referencing them. I feel like this is the most important class which we're gonna have to go through in more detail. So the query and response model essentially is going to have the model spec, because there's going to be quite a lot of distributed work that is going to be happening in this class. Then we have the model layout, logit heads, which is going to be true by default, and we're going to have init scales. So the device is going to be set to glue or CUDA. I think this glue was another backend that was created by Facebook. I'm not sure, but then this one was created by NVIDIA. It's coming from NVIDIA GPU. So I'm just gonna try to verify. Yeah, it was coming from Facebook Incubator. I've never used this, by the way, but yeah. So we have this software device, then we have this layout, which is going to be the layout whereby we know that this took our, it reshaped the ranks, right, based on the number of GPUs and the number of replicas that we have and the number of shards that we have. So it's something like so. So what it's going to do in this case, just is going to create the data parallelism communication given the layout, is going to create a communication also within the replica uh, layout, right? So the replica, we can think of it as an instance of the model, just that has been sharded across multiple GPUs. Then we have this self logit head, which is going to be equals to logit head. So this is going to tell us if we should include the heads at the end of the pre-trained model, right? So we're gonna see that in a second. Then this is just the parameters to load also the model. Then we have this sync params. So you can think of this as like a function that tries to synchronize the parameters of the neural network across different GPUs. Hence, I said, if you want to understand these basics, like things like broadcast, check out my distributed training in machine learning video. So you're gonna understand like all reduce and all of these concepts and in much easier way. But in this case, that's what this is trying to do. And then we have this update model with heads, right? So because of this is gonna be true, so we assume that this is not gonna implement, but if it does, then it's just going to set these unembedding weights to none or the output unembedding to false. Okay, then we know what this does. We implemented this class. It's essentially it's going to take the model and it's going to take the scalar heads, which is going to be the self dot heads that we want to add, and it's going to return the model. Okay. This is def.load. This has to do with loading the model. I think he has to take the path. Yes, there is it here. So it loads the path, which is going to use that, and it's going to get the model, right? Or add uh, some of the parameters of the model or anything that is associated with the model, right? Or model hyperparameters or anything like that. So we're gonna do that. Then we apply this function called update model with heads, which is gonna be just applying the model with heads class. So that's that. Um, yeah, I think that's that. The only thing that's left is just that we need to loop through the heads from the init head. Then we load the weight and the bias of the heads within this parameter to init. Then we apply this sync params given this params to init. So it looks like we just like we synchronizing the parameters with from these Scala heads, because that's what we just loaded here. Um, yeah, I think that's that. So I'd like to kind of like jump into the eval function, which takes the query response and evaluation function, which we're gonna see. I think we're gonna have to understand where is this one coming from to better understand this. But anyway, we send our queries and the response to the GPU or whatever device that we want to use. Then we have this if eval is if eval input is none, then we apply this map nested, which I did not check what it does. Then we get the mask and response from this zero padding tokens. So yeah, this zero padding token is just gonna return the mask and responses. Then we gonna okay, I think now it's starting to make sense that okay, we have these tiled queries and responses and we concatenate them. Now it's starting to make sense why we had to split the query response output in that function that we spoke about. Because I think here it looks like the run tokens are being concatenated. Then we put the model into the state of evaluation. This is necessary for proper evaluation because some layers, such as dropout, behave differently during training and evaluation. Then we set this to no grade. This is a state of a block of code where no gradient will be computed or stored. Then we have this software model, which is going to take our run tokens and then it's going to return the outputs. Okay. Um, then what we're gonna do is that we're gonna have the outputs and be dictionaries. I think we're gonna load a lot of things inside there. Then we gonna loop through the list of number of heads. So this is list of head, and we're gonna include the logits if like the logits is true, else it's gonna be an empty list there. Okay, so this what is it? This reshaped here, what is it? Yeah, wait, this is here. So I'm thinking that this reshapes the output of the head into tensor of what is it? I think it's gonna reshape it into batch size, right? And responses. Then it's gonna be head output shape, a head output shape inside head output shape like so. Mm, okay, so then we apply this function, which is going to take this reshaped. Let's just remind ourselves of this function, but essentially is that function that we went through, I think, in more detail, which is split the yeah. So which means that we are correct with the with the with the dimension because it's just going to take back the number of responses and the query length and query response because we concatenated them inside that function. Oh, look, I'm lost now. Where am I? Okay, it's here. So that's that. Then we have queries.size. Then with this mask, we're gonna return this dimension. Then we have this output. Then we just load this k head with this output here. Okay. If k is in head, we're just gonna say rt.k equals to that's d. So we're gonna load also this inside this variable. I don't know what this rt stands for. The variable, I just can't make sense of it. But anyway, that's what we're gonna store inside there. One thing we just know is that we're storing the result after we've split the output. Just to remind ourselves again, um, you know, there's quite a lot of code to understand here, but yeah, it looks like we're splitting the yeah. This is just the splitting the results. We just like splitting the query length and response. So we are expecting to return a dictionary with the split of query and the response part with the shape of batch query length plus one and the rest of the dimensions. and batch on query length. Yeah, I think that's fine. So actually, it's not that complex of a function. It's not doing something complex or anything like that. It's just like splitting of those. Then we have this eval function. So I'd like to understand this eval function. I think it will be called because this code will be used in like the reward and the policy. So when we get there, we're gonna see actually what which function is getting into which function is getting used so that we can understand. But essentially, I think it evaluates the outputs and gets the evaluation stats anyway. Um, yeah, that's that. So now let's get into this sample function, which I think is the last which I think is the last function into this query and response code. So essentially, what we're trying to do here is that we're trying to sample some tokens, right? So I don't know if you guys can still remember this function that we started with, which is that I think it has to return tokens and log props. We will try to analyze it, but for now, I just want to walk you through this input here. So we have the sample length, which is going to be the length of the response, and context tokens, which will be our input in this case. Then the partial responses, which in this case the author state that it combined query and responses into a new query to be passed to sample. So we're gonna combine these two. That's why here we have just touch dot concat. That's fine. Then I think here we do understand what's going on, which is sending the context type to a device, and we have this model file. Then we take in the end batch and the query length. So that's what we have. Then we're gonna pass the sample. I think this is gonna be the sample hyperparameters. So we're gonna get the sample function. I'm just gonna try to remind you what this was, but it was that sampling function that we had. I think we imported it. It was this. So it's gonna take the parameters like so. So these are like the top P and temperature, and it works in hand with the sampling function, which we spoke about, nuclear sampler and standard. So we have the sampling function, which is gonna do the sampling for us. Then what we're gonna do is that we're gonna have to pass it inside here. So just to remind you why we're passing it inside here was that the sample code that we wrote here was taking a sample function, and we know the sample function was that given the previous prop was just going to return a new token, and then we will use that new token and new logic to calculate the log prop from the cross entropy function that we defined. Then we're going to append these inside these list. Okay, then what we do is that we loop to the sample length. So which means that here we have to pass in the sample length in that function. If I scroll down, we're gonna see the sample length, which is what we have to return in this case, uh, which is what we have to loop. We have to loop through to return, right? So this is gonna be the sample length. Um, then what we have here is the Okay, actually, I was not here. Sorry, I was here. This was confusing because they both called them sample. But anyway, we were here. So what we're gonna do here is that we know that this results return the tokens and log props, and this is what we have inside here. And we're gonna say we're gonna do this asset just for edge cases. Then we sample dot view, which we're gonna set this to this shape, which is badge response per query, sample length, and then we going to pass them into this dictionary here, like so. So yeah, I think that's that. And after we're done, we're gonna return the output after applying all these zero pair. So yeah, I think that's that. Now I feel like we have the a better context of this code. Um, so we can actually try to understand like reward function and policy function and how it works. So yeah, uh, let's try to get into these functions then. So looking into the reward model, before we get into this, just to kind of like link this stuff with like the architecture. So this is what we're going through, like this step two, right? This is like the reward model. So we'll see what it does. So one thing that it has to do, uh, that we know from looking at this diagram, is that it has to take the query, and it has to take this response. In this case, the query will be the post and the response will be the summaries, right? And it has to produce us a score, which we will then calculate the loss based on that, right? So now if we go to where is it, the reward model. So this is the reward model. So essentially, this code defines the reward model class, which represent a reward model for the query response summarization task, right? So the class is going to inherit from the query response model, which is a base class for the model that takes the query and a response as an input and produced output, right? So in this case, a single scalar value, um, which will be the reward value, is going to be computed by the reward head because of, I think we were correct in this code whereby we said that those heads are going to produce the scores, right? So that is going to be the component of the model heads. Then so that's like the overview. So now let's get into like the detail. So starting with this function here, what we're looking at here is that we have a function that is going to take the response token and is going to return the index of the last non-pairing token in each response, because we're saying that response token equals to token, then we're gonna get the first indices of the response whereby it's not pairing. Just to give you a better perspective, this pairing token is -1 because I think we saw it inside here. I don't know if you can still remember, but I'm just gonna search for pairing token just so that you understand how this is coming from. Just gonna look for it in just for a second. Yeah, there's it here. So we define it inside here, and we can see that we use that inside this zero pairing token, in which we were trying to mask. So where we had this pairing, because this is going to return true where there is -1, then we try to set that to 0. So that's what the zero pairing code was doing. In this case, we're just looking for the indices whereby there is no pairing, so it's going to return the indices of the response. So we're going to return that. We're going to see how this is getting used. Then we have this wrapped, what is it, wrap reward model function. So this reward model function return a wrapped version of the function that capture the rewards, right, for each responses. So we can see that this takes two arguments in which it has outputs and it has inputs, which are the dictionaries containing the mini batch tensor of output and input respectively. Then we're going to use this, because of these are dictionary, we're going to extract the reward and response from these outputs MB values. And then we're going to use this getter one function, which is going to get a reward for each response sequence using the indices in the input embeds. This, right? Then we update this output embed reward with the rewards that we extracted inside here. Then finally the ref function calls the original function with updated outputs and inputs. Okay, so some of you may still not understand how this works and what's the intuition behind this. So I think to clear that up, let's get into this reward model code. So this reward takes in the query tokens, the response tokens, in which case we can think of this as a post, and we have a summary. So we need to give a reward, the score of how good this response is, right? So we're gonna return a dictionary containing uh, the reward values of each response as well as evaluation statistics from the eval function. So the first thing that we do is that we use the function called response indices to return the last response indices given the response token, which is I think it is this function here. So we assert to ensure that the queries tokens have the same dimension as like the hyperparameter we define. This is for both the query and the response tokens. We do the same thing for making sure that the query tokens and the response token have the same dimension. Then we have this function called eval, which is if it's not null, then we call this rep reward model. Then we pass in the eval function inside here. So this is used to gather the reward for each response based on the last response indices, right? Then what we do is that we have this results and self.eval. So this self.eval, by the way, because of we inheriting from the response and query class, so it's this function here. Okay, so which was taking the response and the queries and the responses. So we're gonna get our results. In this case, this is what we were returning. Then in this case, we gonna get our results, and what we do is that from our results we're gonna add, because it's a dictionary, we're gonna add a reward in which we're gonna extract our reward give from our responses, and then we're gonna return the results, and the results are gonna behave in the reward function. Okay, the reward values I meant to say. So that's that. So yeah, let's go now to the policy function. Okay, so looking into this policy, so we can think of a policy as looking into this architecture as something that has to take in the input and or it has to output something, right? So in this case, we can see that the policy generate a summary for the post. So it's going to be given a post and it has to generate the summary. So that's what it is to it, right? So um, so before we kind of like get into how it works, let me just start by explaining some of these functions, right? So this is a wrapper function or helper function that is going to take a function and is going to take a list of headers argument. Then it's going to return a wrapped function. So the wrap function essentially is going to extract the responses from the output of the original function, right? So we're going to extract these responses from this output embed key. Then we're gonna assign them to this. Then we're gonna return this as our response, right? This might not be intuitive enough for now, but let's just get into the code and we're gonna see how it's getting used in this code. Um, so some of you might still remember this function, which was the sample function. So essentially, we know that the sample function was that given the query token, it's gonna generate tokens, gonna generate the response. So hence you see it takes parameters such as a sample length because just to remind you, what we did was that we needed to loop through, right, so that we can generate the response. So if you can remember the sample length, so we're gonna generate the response for the sample length. And what we do is that we keep on appending the tokens inside this tokens list, right, and the log prop. And we know that this function is gonna have to return log prop and the tokens, and that's what we have here. Okay, and the extra outputs, that's what it is. I think these represent the values, and this is true because we can see that the author also state the same thing, that we're going to have the token, which is going to be the batch number of response and the response length. Okay, so that's what it is to this. Then we asset the self.logit head. Then we have this sample function, which is going to return a dictionary. Is it a dictionary? Let me see. Yes, it is a dictionary, which is tokens, log prop, and value. Then we're gonna return them here. But the idea behind this is that we're given a response, we're given a query, and we have to return the response. In this case, which is returning those tokens, which is gonna be a response. So we have this eval, which is going to be um, the function that is going to be evaluating our 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 policy. In this case, we can see that these are just assertion functions. So let's just get into that, just making sure that we have the right dimensions. Uh, oh, this query and response have the same dimension. So what we can see here is that we have this eval function, which we're going to evaluate our response and we're going to evaluate our response given the query, right? Then we're going to return the results. I think this is going to contain the evaluation statistics. Looking at this eval here, where is it? Yeah, it's gonna be here. So yeah, eval statistics, and just to yeah, it's gonna tell us yeah, it's gonna tell us if this was the correct response given this query token, right? So yeah, I think that's that. I know that like how I explained some of the things might not have been intuitive enough. As much as I was also trying to wrap my head around certain things, I won't lie that I quite find this to be it was quite challenging at some point to kind of like wrap my head about certain things. Um, but yeah, I hope I was able to kind of like maybe clarify certain things. I'll link the code in the description below, so that you guys can probably, if you want to drill deeper into this and try to digest the paper and the code yourself. I'll really appreciate it. Let me know, guys, if like you enjoy this type of walkthrough and code, and I feel like we might not understand everything as much as that's how code is like, right? Like it was written by somebody else and they had a different thinking when they were writing it. So we just, and some of the stuff you can, as you can see, that like it's not necessarily commented, so you just have to make sense of everything. And the paper is just like a high level of implementation, right? So but what we try to do is that we try by all means to understand what was it that they were trying to do, right? So, but yeah, if you enjoy this type of like walkthrough, let me know so that I can start making them more and deliver them to you guys. So yeah, so that we can all learn about this stuff, right? So I covered all the important stuff and all the stuff that I didn't cover, such as utilities. I feel like these like were about like testing and like logging. So I didn't cover these things because I needed to cover like the actual core of the paper. So yeah, I feel like these were more of like they're still important, but I feel like these maybe if you guys want me to cover such things like utilities, it's fine. I'll do that. But yeah. But anyway, without wasting any time, guys, I really appreciate it. I'll see you in the next one. Thanks. Bye.